Alright, so on the back side of this, of our notes here, talking about electrochemistry, I want to go over the two different types of cells that you're going to see. So we have voltaic cells and we have electrolytic cells. But before we get there, let's kind of review a few of our mnemonics. Now we've got Leo, Ger, and oil rig. Do you guys remember those? Okay, does anybody remember what they stand for?
Oxidation is losing, reduction is gain.
Okay, well let's write them out. Now there's oil rig, some people like that. I like Leo Ger better, so I'm going to write it out right here. Leo the lion goes Ger. Yep, if you lose electrons, it's oxidation, yep. And if you gain electrons, it's reduction. Alright, so Leo the lion goes Ger. I'm going to teach you about two other ones that are going to help you remember this for electrochemistry. So off to the side, let's make a little T-chart. I'm going to write the cathode and the anode. So the cathode is going to be one side and the anode is another. Now if we're talking about electrochemistry, one of the things we just mentioned was batteries. So if we were to draw out a battery, what do we know about batteries? So there's a positive and a negative side. What else? Okay, it has charge. Well, what is charge? Okay, voltage. Voltage is made up of electricity, which is made up of electrons, right? Perfect. So all these little electrons are stored up in your battery. The question is, though, which one is which? Alright? So I want you to think of your cathode has a T in it. What does that T kind of look like? A plus sign. Yeah, exactly, like cations. Cations are positive, right? There you go. So put a plus sign on there. Anode is going to be negative, right? Anions, negative. So you have your positive, you have your negative. On the battery, sometimes you see a little bit of a kind of nub like that. Say what? The nub's there to kind of help with the connection. And after we do the cells, I'll actually show you why. But we'll get to that. So we have our battery. We have our positive and our negative side. What we need to figure out, though, is reduction and oxidation. Which one happens on which side? Okay, so on the cathode side, I want you to put a little star. I want you to put red cat. On the anode side, I want you to put a little star and put an ox. Right, so we have red cat, we have an ox. Now why, Mr. Hill, why do we have all these animal-themed mnemonics? Well, it's a good question. I don't know about you, but it helps me remember. Dude, go for it. So yeah, so the cathode is the side where we have reduction. Anode is the side that we have oxidation, yep. Great. So there's a red cat, we have an ox, we have a Leo that goes Ger. How many of these are we going to have? Well, we're going to add another one. you'll see, how do we figure out where electrons flow? Electrons are going to flow from A to C. Okay, so we have electron flow. Electrons flow from A to C, because it's in alphabetical order. So they're going to flow from the anode to the cathode. Right? Now let's kind of extend this line down just a little bit longer, because we're going to add things on here as we go through today. Okay? And then draw a line right about the half mark. And let's go underneath here. So we have our page at the bottom. Let's put like this two sides right here. We have half of a half, so let's put this into fourths. Now we have two types of cells. One of them is going to be our voltaic cell. Sometimes they call it a galvanic cell. And the other one is a electrolytic cell. Now we have voltaic cell with volts, right? We've got electrolytic cell. Now electro, we can break down to, electricity. We kind of know what that is. Now where have we seen lytic before? Where have we seen maybe even lysis? Maybe that'll ring a bell. There's what? Okay. So lysis, where have you seen things lyse? True, but what about the cell? So way back in bio, so what do lysosomes do? They break things down. Exactly, like they break it down. Exactly what that is. So this is using electricity to break things down. Okay, don't you just love Greek and Latin roots? They're awesome. Helps you figure out what things actually mean. So if we go to our voltaic cell, here's what I'd like you to do. Let's draw two cups. So we've got a cup here, and a cup here. Make them pretty big on your paper. So just to see, see it a little better. Now we've got a bridge from one to the other. And I'm actually going to literally call it a bridge. It's going to be a salt bridge. Yeah, so salty. Just like some of you. Excuse me? So here's a point. Literally a point on the AP test. If you start drawing this out and you label a salt bridge, you put salt bridge on there, +1. I kid you not. I think it was the 2013 AP test. They said, did they label salt bridge? +1. So make sure you do this every time. Draw your cups and be like, something bridges between them. Oh yeah, that's a salt bridge. Okay, now what is salt? What's our kind of formula for salt? Na. Okay, so we could use Na. Why not? Let's do it. Put Na and then Cl. So you could use NaCl, you could use KCl, potassium chloride. But let's just stick with what we know, because we don't have to think too hard to kind of come up with that one. Just table salt. Right? Now you're going to have two pieces of metal. One piece of metal here. One piece of metal here. And they are going to be connected by a wire right there. So I'm going to label these guys as like the type of metal they are. So let's say this is silver. Let's go right here. And let's say this guy is copper. Now we're actually going to be making these cells. And they're going to look like this. So when we make these on Thursday, they're going to look a little different from the one that we're talking about right now. Right? Because what happens is we'll have these pieces of metal. Right? We've got one type here, we've got another copper on the other side. But inside our two cups, instead of using two cups, we're going to use one placed inside the other. See how that works? So we're going to have kind of like a cup within a cup. So it's like cupception. Yeah, exactly. Right? So it makes it a little more self-contained than if we had like two cups and then a salt bridge and then we like electrified it. Okay? So just so you guys know where we're going with this, we have a cup that's kind of shaped this way instead of two cups like this. It's just cups within cups. Okay? Kind of like the Russian dolls, the babushkas. Right? Yeah, so just kind of put that on your radar. It's going to look a little different than the one that we're drawing right now, but it's going to be the exact same idea. Okay? So with voltaic cells, we have metal, salt bridge, and we have some liquid in here. So I'm going to draw this for the liquid. These solutions are going to be made up of these ions floating around in solution. So these aqueous solutions are going to be like Ag, what's a good one with that? We'd say silver nitrate. How about that? AgNO3. Right, now when it's aqueous, what do? They separate, right? And what do we call that? They dissociate. So this is going to be a lot of Ag plus and NO3 minus ions just floating around. Right, now this is important for later. See, there's those planes. Isn't it great to be in a military city? So, copper on this side, CuSO4. Now here's our polyatomic ions quiz. Sulfate was the charge. Adriana, I know you want to answer this. So it's a plus or minus? A -2, right? So we've got SO4 -2 floating around, and we've got a Cu +2 floating around in our aqueous solutions. Okay, now why is it important that they're similar to these guys? We'll see as soon as we track down those electrons. Okay, now notice, do we have a power source? Do we have any, like, is it hooked up to a battery or anything? No, so down right here, put no power source. And let's pause this. Okay. So there's no power source. Underline that, por favor. Now we have to figure out where the electrons are going. The cool part about having a track like this is we know they're either going this way or they're going this way, right? Now if we have to figure out which way they're going, let's go ahead and flip to the back of the first page. What are these guys? Yeah, you do, back of the first page. Now what is this? These guys are, what does it say at the top? Half reactions, and above that they are reduction potentials. So what's cool about this is that this is what allows us to figure out what the potential of each metal is for being reduced. Now, being reduced, remember, is Ger, so gaining electrons reduced, right? So what's the potential for these guys to gain electrons? Who wants it more? Let's find out what our metals were, right? We look at our metals, we have what? Silver and copper. So I'm kind of simplifying this here, but I want you to think which one wants the electrons more. So let's find each one. Where's silver?
Under mercury of iron.
Okay, so right here. There's silver. Where's copper?
Under SO4, above SM.
Okay, so there's different types, right? We've got a copper here, we've got a copper here.
We have to use the one that's aqueous.
So, yeah, what do we use? We have to use the ones that's aqueous, because it's turning into a solid in this case. And this one's turning into a solid here. So let's, just for the sake of comparison, let's use the one that's the same from aqueous to solid, right? So which one's up higher on the chart? All right, we've got silver at 0.8, we've got copper at 0.3. So let's flip back here. Again, simplifying this majorly, our silver, we said 0.8, our copper is 0.34. If you're an electron, and I'm going to pick a different color here, I'm going to make my electron path blue, and you're on copper, on this wire, if this one's only 0.3, and this one's 0.8, he's going to want to go towards the higher number. So that means he continues all the way through, goes up the salt bridge, down through, and all the way around. So I'm going to put this as our electron path. So now that we figured out the electron path that goes this way, which one is the cathode? Which one is the anode? If it's going from A to C, that means it's going from A to C, so this has to be our anode. This has to be our cathode. Okay, now what does that tell us is happening at each of those spots? At the anode, we know that oxidation is occurring, right? At the cathode, reduction, exactly. Now what causes this to move this way? What causes it to go that direction? Our reduction potentials. So down here, let's put reduction potentials cause electron movement. Right? Our reduction potentials cause electron movement because it's the potentials. Yeah, there's no power source. No power source for the voltaic cell. Okay? Now let's think about what this does to the ions. So we'll zoom back in for a little bit. If you're an electron, you're coming through here, going this way. If you want to go from here to the other side of the salt bridge, the magical salt bridge rainbow, how do you get past from one side to the other? On this side, you're going to, if it's NaCl, you're going to have then Na plus over here and kick out on the opposite side, so you'll travel through that electron, and we want to get rid of the electron on this side, so that means there's going to be a Cl minus on this side. So you guys see how that works? If you want an electron to pass from here to here, kick out an electron through Cl minus on this side. Now, here's something that's kind of interesting. Do you guys ever see batteries that have, right here, let me pull one out real quick. Do you guys ever see batteries that are old, and they kind of have like some kind of gunk on it, and it's like really crusty and gross? So that's caused by it, but what ends up happening is, a lot of times it happens in humid places, or if there's a little bit of a circuit, and it kind of short circuits, what will happen is you'll get oxides, like kind of like rust, because rust is iron oxide, and you'll get these different buildups right next to the metals, right next to your cathode or anode. Now what I want us to figure out is, which side does it usually build up on? Alright, so go back up to our cathode and anode, a little T-chart there. Put a little bullet point on each side. The buildup of oxides is going to happen at our cathode. Buildup of oxides. And our anode, we're going to have our metal electrode decreases in size. Now, I used to put the metal electrode gets reduced, but I was like, wait, no, it's oxidized. Oh my god. That would always throw me for a loop. So I'm trying to word this in a way that we don't mess it up. So we have oxidation at the anode, but it's going to decrease your metal electrode. Because what happens is, when we have these electrons running around, run around, our cathode, let me pick a different color. So I'll use green in this case to kind of show the buildup. This cathode is going to end up getting lots of that buildup on the sides. So all around this guy, he's going to have a lot of those little spiky crystals. Yeah, what's up?
So during the experiment, would it happen in front of us, or would it happen over time?
So it will happen over time. It won't just be like instant, because there's no power source, so this is going to take a little bit. The galvanic cell that you guys are going to make, like this guy right here, you're going to end up getting probably like a 1.5 volts. So it's not very strong. Yeah, so if you, exactly. So if you want to have, like, even just take this battery, and like if we're taking a look, see if we can find it, if it'll say it. So it's AA, right? Check out this one. I don't know if you can see that. Oh, I can see it better that way, right? So you have 1.2 volts, right? Now, we won't get into the whole, like, volts versus amps versus watts versus all that. We're not going to do that right now. But the amount of volts that you have, think of that as, like, the amount, well, let's not get into that because I don't want to confuse you. But it's how much. At this point, just think of it, volts is how much goes through. So if you look at your sockets at your house, or like the sockets over here that you plug stuff into, those are, does anybody know how many volts are going through those? So yeah, 110, 120. Sometimes, depending on your house setup, you're going to have like a 220. And so that's going to be very different. And you can see how things, Carly, see how things are going to go a lot faster. So this will be like really slow. What we're going to do here is going to be really slow. It's still going to happen, but it will happen over time. So we won't be like making jewelry right here, but it's something that is how they make different platings. But they do that through the electrolytic cell, not the galvanic or voltaic cell. Okay? Cool. Any questions on this one? Go ahead. Okay, yeah, so the crust is going to kind of build up on this cathode, which means this side, the anode, it's going to slowly chip away. So it's going to kind of dissolve and make more copper plus 2 units. So there's going to be a lot of different pieces. Think of it as pieces going into solution. Whereas this one, a lot of these Ag plus ions are going to start attaching to it. So this one's going to get bigger, and this one's going to get smaller, until eventually this one wastes away. Sound good? Kind of. Okay? But batteries, again, they work like this, but they're set up slightly different. Okay? Because we don't have like, here's a battery and we come out with 2 cups. Right? So let's go to our electrolytic cell. I want us to kind of think of the same setup, except we're going to have a power source. So put a little star up at the top and say, power source. We've got the power. Okay, for our electrolytic cell, we do have a power source, but it's going to be set up much the same way. We're going to have those 2 cups. Of course we'd have the 2 cups. Why wouldn't we? Oh, you know we're going to solve bridge. We've got the bridge to the other side. The bridge to terabithia here. And we have our electrodes, the pieces of metal that get stuck in the solution. Electrodes, electrodes. The big difference here, though, is we're going to have a battery at the top. So the way I want us to kind of write the battery, if you want to put a box and just put, you could just put battery, and that works. But as you do diagrams, if you want to be like professional about it, kind of like have a small line here and then a bigger one here, and then have it connect. The only thing you've got to be careful with is that this actually tells you which way the electrons are flowing, which, when we're drawing this out right now, we don't know yet. So maybe put a box for battery, and then we'll put that in there. But I did give you a clue just now, if you know anything about designing those. So what else do we need? We've got our salt bridge. Did we label that? No. Would we have missed out on that point? Yes. If they ask you to draw it more than once, yes. They're probably only going to have you do one. Okay, salt bridge, which in this case, let's use NaCl again. Pretty much, salt bridge and resonance, right? Okay, salt bridge, NaCl. We've got our solutions. Let's just use the same electrodes, so we'll use silver on this side, just to kind of keep it consistent. Silver, we've got copper, and then we've got AgNO3 floating around in here. We've got CuSO4 floating around in there. Alright, I think we're about set. So let's think about work. If we need to do work, that usually takes energy, right? Because in order to do work, you fight against some kind of force, right? So if I have like this pencil on the ground, or this highlighter right here, if I want to lift it up, I have to put work in. I have to put in energy to fight gravity to lift it up. Right? So, because right now, it has zero kinetic energy. But if I lift it up here, what kind of energy does it have? Potential energy, right? So I'm storing the energy up into it till I release it as kinetic. So it's the same kind of idea of like energy transfer. In order to change something from the way that it's normally going, like for instance, see how this one, we have the electron path normally goes this way. If I want to flip that, I would have to provide energy for it, right? Because instead of going this way, if I want it to go the opposite direction, I would need to provide something to have it fight against the natural state. So in this case, if we have a battery, that's going to provide our energy for it. And so we can force the electrons, that's an arrow, I promise, to go this way. And go against kind of the natural order of things. So why would we care? So this is actually really cool because a lot of, for instance, you ever see those nice old cars that have like chrome bumpers? Yeah, exactly, like the 50s ones that are like really nice looking and all shiny and stuff. Those are actually iron bumpers that they put in chrome solution and they electrified it to kind of plate it. So they did what's called, I'll put a little asterisk here. Yeah, exactly. I was just going to say plating. Because you can gold plate stuff, you can silver plate stuff, you can use this to plate anything. Now what does plating mean, just to kind of take a step back? Yeah, you put a thin layer over whatever the base metal is. So it's a nice way to kind of, if you have really kind of crappy metal and you want to make it look nice, you can have this huge amount of just really cheap basic metal and then put like this tiny little layer of like expensive metal on top. But that's the part that's on the outside, so what does everybody see? Everybody sees just the nice expensive layer. So you kind of see how that works? So that, David, that's probably one of the best reasons to think about this, like why this could be important. Go ahead.
Don't they also use it to remove rust off metal?
Yeah, there's tons of different applications. You can do all kinds of stuff. But realize, if we, just to use your example, if we're creating oxides and kind of rust by sending it this way, what would happen if we reversed it? All of that stuff would then go into solution, which would reverse this reaction, which would kind of make it cleaner, right? So in terms of thinking it as clean versus non-clean, that would kind of clean it off a little bit, and it would make us have more of a solid on this side. Okay, so we just kind of flip it back. Now, obviously, there's lots of different layers to that process, so it's not going to exactly work back and forth the exact same. But just to kind of give us a basic idea, yeah, that's exactly what it'd be for. Okay, so we've got plating. Now let's label our sides. Which one is the cathode? Which one's the anode? What do you think, Kim? Cathode and anode. How can we tell which one is which? It's flowing from A to C. Which one's the anode? There you go. Anode for this side, yep. So the cathode is copper, yep. Anode and cathode. So you see how they switched? In this case there's the cathode, in this case there's the anode. That's probably the hardest part about electrolytic versus galvanic cells is realizing that your electron path goes completely different if you add a power source. Why? Because this is the natural order of things, right? Things naturally will do this. Why? Because of your reduction potentials. But you can force it to go the other way by including that energy and helping it do that work. Okay? Which would leave us with what kind of ions floating around? If you want the electron to pop out this side, yep, Cl minus on this side. And this side would have an Na plus. Now which side would have your buildup? Alright, because last time the cathode was your silver, and there's a buildup, always a buildup on the cathode. So in this case, our cathode is copper, so we're going to have a buildup around here. And our silver is going to slowly start chipping away. It's going to get little pieces kind of pulled out of it as it goes to solution. Kind of like Swiss cheese type. Till eventually it kind of withers almost completely. Yeah, depending on your power source, that could happen really fast or it could take a long time. Okay, any questions on our electrolytic cells versus our voltaic cells? Go ahead.